Well, hello there. I assume you're watching this video because you need a little nudge on this problem with the two plates. And I will tell you, this is a challenging problem, but it's such a cool application of Gauss's law. I just think it's a great, if somebody shows you, it's a great example of how this little trick can take what would be maybe a really complicated problem and just eventually get there to an answer. So we've got these two plates, and they're not traditional parallel plates like a capacitor would be because they're not equal and opposite charges. They're both positive, and one of them is twice as positive of the other, or as the other. When we're all done, we're going to realize that there is some polarization going on, like sort of a mutual polarization where this charge up here causes this plate to polarize and vice versa. But we don't need to know that now. Eventually, when you're done, you look at all the charges on each surface, because that's one of the things they'll ask you for is, what are all the four surfaces charges? They're not the same charge on each plate, okay? So they separate a little bit. But anyway, we'll get there. They ask you first for how strong the electric field is in these 5 different regions. Now, 2 of them are super easy. I don't want to give too much away, but when they ask you about region 2 and region 4, which are like the actual metal plates themselves, if we could burrow into the metal and we're surrounded by it, asking how strong the electric field is inside the metal is actually what we call trivial. It means it's so easy you don't even need to calculate anything. Okay, I don't try not to give too much away. Now outside, in region 1 or 3 or 5, that's a little bit different. So the first thing you have to recognize is that because these are flat sheets or plates of charge, that there is a uniform field kind of radiating away from them, and it will be the same everywhere. It's not dependent on distance, okay? Now, that's significant because that means up here in region 1, I have the exact same field as I have in region 5. Like I could flip the plates over and it would be the same field. That's because each plate is kind of creating the same field above it as below it. And so up here, you're sort of outside both of the plates, okay? So when you draw a Gaussian box, this is what you draw when you do a planar symmetry Gauss's law problem. You draw a Gaussian box. I've seen it drawn like a round-based box, which is just a cylinder, but I think this is easier. So just draw a little box, and it goes through the entire arrangement, okay? Now I'm going to draw in green what these field lines would look like, and just a representative sampling of them. Okay, up, and away. And then down here, we would have the exact same field. So again, I'm finding 2 fields at the same time. Later, they'll ask you for field 5, but you just know the field is going to be the same as what you get for number 1. But you kind of have to do them both at the same time because of how Gauss's law works. Gauss's law says, I think this 3D version just looks a little better for what we're doing. It is just a 3D version of what looks like this. So Gauss's law says, if I have enclosed some charge inside this little imaginary, it's red, I don't know if you can tell that on the video, this red box, then any flux that pierces through any of the surface area, and I hope you can tell there's only 2 of the 6 faces of my Gaussian box that have any flux through them. The top face here and the bottom face down here. Both of them are outward types of flux. That's the positive type flux. The sides have field lines skimming by them, but not piercing through them. So it doesn't count as flux. So these 2 have my flux, and that flux is determined by the amount of charge that I have enclosed inside the box, which is not all of the charge on the plates, but it's proportional to them, okay? So now I'm going to actually write out kind of the formal, I told you in class, this is a good way to start. When you're doing an AP problem, start with something fundamental that's on the green sheet. This is, I think, equation 34 if you're using my sheet in my class. Other people might be watching this that don't have a numbered sheet, but hopefully you have the reference sheet that has this on it. It's called Gauss's law. And then you quickly get rid of the calculus-y looking stuff, because when you do Gauss's law right, you typically don't need to use calculus. So it's the electric field, the one you're looking for, that's like what we've represented by these green arrows here, times the area through which that flux is piercing. Well, what is that? That's two areas where, let me just label it here. A is like the top of the box, that area. So many square meters or square centimeters, something like that. Again, all in your imagination we're doing this. So weird, Gauss's law, isn't it? Okay, I'm going to put my epsilon sub naught down here. And then it's like, okay, how much charge have I enclosed? Well, we've got all this charge plus Q on the top plate and all this charge negative Q on the bottom plate. So the amount that we've enclosed just depends on the charge density and then how big that box is. So I'm going to write this like I traditionally would with most. I don't love that they've given you letters here that you have to use, because like A, for example, that I wrote, that's already one of the parameters in the problem. I really wish Dr. Knight had not chosen A for this, but it's okay. This will get us through. In fact, let's be careful here. Let's say this is a G for Gaussian box, okay? Then we're not getting things mixed up. All right. Okay. Now, how much charge is inside the box? Well, it's just the fraction that is enclosed in the fraction of the whole charge that's enclosed within this box. So that means all the charge times just the fraction of the area in the box to the fraction of the entire plate, or to the area of the entire plate. Okay? The part of the area in the box to the area of the whole plate. So let's write it this way. All the Q times that fraction of the box to the entire plate. A sub G over A. All right? And that's one plate. But then we also have charge in this bottom plate. And that's got twice as much. So we have Q plus two more Q. So what I'm going to do is I'm just going to combine these. It'll save me a little bit of writing here because I'm a little crowded on my paper. So all the charge on both plates together is 3Q. And then I've just picked off which portion is inside the Gaussian box, all right, by using this fraction, the area of the Gaussian box, which is this, to the area of the entire plate. Okay. Now I'm going to simplify some things. I'll use red so it sticks out a little bit better. The A sub G here and here cancel out. And I just need to move the 2. And we get, I have 3Q on top, and then I'm going to have a 2 and an epsilon sub naught and an A. Again, that's the area of the whole plate that was given in the problem. That describes the electric field. Again, we're talking about in region 1, so maybe I'll put 1 here. But that's also region 5. All right, we just did 2 problems at once. It's wonderful. Okay, I'm going to pause here. Let maybe you pause there because we just did a lot there. And I fumbled around a little of it, but I think it's good enough for you to follow. And I'm not going to do all the parts this way. This is a really big step to get started. So why don't you pause here for a second, kind of soak that in. Jot down on a Post-it note if you're watching this at home, like, okay, where did you get confused? I need to ask the teacher about this, okay, and get things clarified. And then we'll start and talk about the next step. Okay, so we're going to move on to the next part, which is finding the field in like the middle of the sandwich, if you will. So we just figured out fields E1 and E5. That's like outside the whole arrangement. And I am not going to draw that 3-dimensional version because I think that's a lot, especially, drawing things is not easy when you're first getting into it. So I'm going to draw the 2-dimensional version of this. And so instead of looking like an actual box piercing through there, it'll look like just a rectangle, okay, in 2D. So we found E1, E3 is what we're going for, and E5 we found as well. Now remember, E2 and 4, those are the ones I say are trivial. And if you don't know why they're trivial, ask your teacher. I'm not giving it away in this video because that's just the answer to one of the homework problems. A big hint is you're in the middle of the metal there. That's the key. So now I'm going to use my answer from this part, from E1, and I'm going to use it to find the field E3, Okay, so now when I draw my little Gaussian box, it's going to be the same kind of thing. It's just a box exactly piercing straight down through that plate so that my field runs right along the four sides of the box and pierces directly through the two end caps of my box, okay? Those are the areas I called A sub G. So you got a picture, again, what we just found, E1, that's this. I'm representing it that way. E3, I don't know how strong it is, that's what I'm after, but I do know which way it points. Because if you remember, this has a positive, let me draw this in black, a positive 2Q, and the bottom is just a positive Q. Let me make sure that's right. I set the problem up earlier. I want to make sure that's right. Oh, sorry, the Q's on top. Oh, all right. So this is 2Q. Okay, so we're going to then look at this and say, all right, if we've got more charge under here, oh, this focus is terrible, isn't it? So we've got more charge down below than above. And these are electric fields. They're vector kind of quantities. And in this case, they're both going away from the respective plate that's making them. So we've got a bigger upward field going away from this plate than we have a downward field here. So that means we have to have an inward flux, E3, inward, into my Gaussian box, okay? By the way, in case you're wondering, you can do this exact same derivation using a box down here that goes through the bottom plate, and in that case, you'll actually have an outward flux, all right? Yes, it will still give you the same answer. E3 is still able to be found from either one of these. So now, because I know E1, I don't know E3, but I do know the charge that I've enclosed, okay? So let's write this out. I'm not going to write it out as formally as I wrote it out last time. I'm just going to say that my flux, let me write it this way. Flux, this is the symbol we use for flux, is the enclosed charge over epsilon sub naught. Okay, now what's my flux? For these two faces, it's now a subtraction expression because I've got positive outward flux here at the top plate. So that would be E1 times the area of that little Gaussian box. I called that A sub G before. And then I'm going to subtract this inward flux. It's really, in vector language, it's adding the opposite, right? But mathematically, you're subtracting. So that's E3 times that same area. You make the boxes nice and, I guess, symmetrical. Okay, now, what is Q in? Q in does not include both plates like it did in the previous part, just the charge on this upper plate, which of course depends on how big my box is. So I'm going to do that same little fraction trick I did before. So I'm not doing the whole plate's charge. It's not Q. It's just the part that's been enclosed within my little Gaussian box that I drew here. So that's this fraction. So it's all the charge times the fraction that's in the red box. That's A sub G over A. Okay? And then I have to remember to put it over epsilon sub naught. All right. Now, I'm not going to go any further because at this point, you should be able to substitute in the expression that we found in the last part for E1. And it will combine nicely with this. And then you will solve for E3. Okay? Solve for E3. And you will get an expression. It will come out positive because I already knew the direction. So when I already knew the direction and I accounted for that by subtraction, I don't have to wonder if it's going to come out positive or negative. Okay. Sometimes with some vectors, you're not sure what it's going to be until you're all done. All right. So that will take care of the last little region, the fifth of the five regions for the electric field. So now I'm not going to do the last part for you, but here's what the rest of this problem asks for. What are the actual charges on the four surfaces? Not just the whole plate, but like the top of the top plate. I think that's called region A or plate A. And the bottom of the top plate, they call like surface B. And then we've got C and D for the bottom plates. So you can find all four of those. And again, the result of this is amazingly cool. If you understand polarization, it's like, oh, that totally makes sense. But I don't want to give it away because that would spoil it for you. So let me give you the strategy for approaching it. It's another Gaussian box. So it's Gauss's law, but this time what you do is you draw a Gaussian box that only goes partly into the metal plate. So here can be the Gaussian box we could use to find the surface D charge, okay? And the trick is this. Since you now know, or you should have solved for all 5 fields, you now know the field here and here. That means you know an expression for all the flux. Like before, we were solving for something on the flux side of the equation. Now we know the flux, so we can put that in there. And what we're solving for is how much charge is inside that Gaussian box, the little blue one I drew here, which notice is just the bottom surface. So this would be the charge on plate D for my box here. And if you drew a different box, let's say up here, then you would get plate C. And obviously, the plates up here, you could just draw a different Gaussian box. So those are all doable. And again, I'm not going to do it for you because that's way too much work to do for you. So you can work through that, try to figure that out. And when you're all done, if you're in my class, we're going to have a conversation about it. If you're in somebody else's classes, go to that teacher and say, oh, this result is really cool if you ended up getting it. And look what happened to the polarization of these plates when they were near each other. Okay, so no spoilers there. I'm going to turn you loose. Hopefully this was helpful. I know it was a lot, but I'm not going to charge you any extra for it. So, all right, good luck with the rest of that. Thanks for watching.